Hi there guys, welcome to this video where we're going to take a look at another interesting problem from mathematics, and we're going to take a look at the problem solving process. What kind of approach might we need to take when it comes to solving or trying to find a solution to a fairly non-routine problem. So the problem that I've chosen for this video is quite a challenging problem. It's from this book, which is Linear Algebra and Geometry by David Smart. This is an old textbook for the A-level further maths as it was in about the late 1980s. So it's an old textbook, but it's a really, really good textbook. And when I was doing my A-level further maths, when was it, 2004, 2005-ish, this was a textbook that I carried around with me everywhere. I used this more than the textbooks that were actually supposed to be for my course. So this wasn't one of the textbooks that was supposed to be for my course, but I got hold of a copy of this through my my A-level further maths teacher, and I spent more time working from this one. I found it really interesting, and it had such a big influence on my development. My mathematics development. I'd really recommend it. It's maybe not easy to get hold of now. I'm not quite sure, but it's a really good textbook. And by the way, if you are doing GCSE Maths, A-level further maths, and you really want to challenge yourself, you really want to push yourself, what I'd really recommend is that you explore the resources that are available to you. Really cast your net out and see what's available to you. Older textbooks, in my opinion, tend to be really good quality. They're much more, there's much more substance to them. I find that a lot of the newer textbooks for GCSE and A-level maths are they're very flashy in terms of the lovely pictures that they contain, but they don't emphasize what to me is the most important skill to develop in mathematics, which is problem solving. A lot of older textbooks really do introduce some challenging problems and really do emphasize that problem solving aspect of mathematics. Anyway, the problem that I've chosen is from page 118 in this book. Problem number 7 from page 118. So this is quite a long problem, and this took me quite a while to really figure out. And this is normal for problem solving, that if it's a good challenging problem, it's something that you've really got to chew things over with. The solution doesn't just fall out onto the page. If it does, either you've been really lucky or the problem was just far too easy. But even if you're fairly familiar with a lot of the concepts, the techniques that are ultimately going to be involved in the solution to that problem, it still can take a while for you to figure out how exactly you're going to put those pieces together in the right way to solve this particular problem. So what we're told, so this problem involves matrices. So it will help if you are comfortable with the idea of matrix. I'll be using determinants of matrices, particularly 2x2 matrices. And matrix multiplication would be useful. Obviously matrix addition, although it doesn't come up too much in this, it might be useful. As long as you're familiar with many of the basic properties of matrices, general matrices, then this shouldn't really present too much difficulty in that respect. You've still got to figure out, so we're going to be introduced to a new type of matrix, or a particular type of matrix, should I say. And through solving this problem, we're going to gradually reveal some of the particular properties of this category of matrices. Okay, so the type of matrix that we're going to be interested in is what's called an idempotent matrix. It doesn't matter if you haven't come across idempotent matrices before. If you've if you dealt with matrices, you know matrix multiplication, you know that about determinants and things like this, then idempotent matrices are just a particular type of matrix. And this is quite common. If for example, if you're looking to go to maybe a high-ranking university to do maths, or a maths-related subject, so Oxford, Cambridge, Warwick, something like that, where you've got to sit the MAT, or you've got to go for an interview. At some point along the application process, what will probably happen is that you'll be introduced to some concept, some mathematical object that you haven't encountered before. And what I wouldn't recommend is that you try to figure out what that's going to be, or that you try to learn everything about mathematics before you go for your interviews and things like that, because the thing that you'll be presented with may be something that has just been cooked up by one of the interviewers a few days before, or something like that, a particular type of mathematical object. And what you're expected to do is to take that the information that you're told about that object, what it is, and some of its basic properties, and then you're expected to logically deduce more and more of its properties as you go along, to a certain extent. So sometimes what will happen is, particularly with some of my students in the past, they might be presented with something new. So they know how to, let's say, I'll use this as an example. Let's say they know about matrices, and I introduce them to the idea of idempotent. Some of them, in some cases, their immediate objection will be, well, I've never been told about idempotent matrices. I don't know anything about them. Okay, well, I'm telling you what an idempotent matrix is, and I might give you a few of its basic properties. I might not, it depends. It might not be necessary for me to do so. But what I expect you to do as the interviewer, or if it's on the MAT exams, the examiner, what I expect you to do is to realize that you already have various techniques that you can use, that you can apply to this new concept, to start to see it from different perspectives and to deduce some of its properties. Okay, so it can't be an objection necessarily that just because you haven't encountered this thing before that you can't work with it. That's what you're being expected to do ultimately. Okay, so what we're told here is that we say that A, the matrix A, is idempotent if A squared is equal to A. So A squared equals A, where A is a matrix. We're not set a particular size to the matrix at this stage or anything like that. We're just told it's a matrix. Okay, so then we're told if A equals A, B, C, D, where A, B, C, D are real numbers, and that's going to be relevant to us at various points throughout our calculations. A, B, C, and D are real numbers. And then we've got three cases that we need to consider. We're going to do them one at a time, obviously. The first case is that if A plus D is equal to 0, show that this implies that B equals C equals 0. Okay, so I've got a few notes at hand for this because it's quite a lengthy calculation. And I've just got my notes to refer to remind me what I need to do. Okay, so let's have a look then. So if A is idempotent, that means that A, B, C, D times A, B, C, D, which is equal to, doing matrix multiplication, A squared plus BC, C times A plus D, B times A plus D, and D squared plus BC, this must be equal to A, B, C, D. So what it means for two matrices to be equivalent is if each of the each of these entries in this matrix match up exactly with each of the entries in the second matrix. So this entry has to be numerically equal to this entry has to be numerically equal to this entry. So that gives us a series of equations. A squared plus bc equals a. B times a plus d is equal to b. C times a plus d is equal to c. And finally, d squared plus bc is equal to d. Now, it might be tempting at this stage to cancel through by b here or cancel through by c here. That's not the right thing to do because we don't know what the value of b or c is at this stage. In fact, we're wanting to prove that b and c are both equal to 0. If we knew that b or c were non-zero, then yes, we could cancel through. That's going to be something that we might need to do further on. But it's not something that we can do at this stage. Because if we did that, by the way, if we did cancel through by b here, we'd get a plus d equals 1, which would exactly contradict what we're told here, that a plus d is actually equal to 0. And in fact, it's this that we need to use here, because if a plus d is equal to 0, that means that b times 0 must be equal to b, and that implies that b equals 0. And similarly, doing more or less the same calculation, the analogous calculation here, c times 0 equals c implies that c equals 0. Bingo, we've got it. B and c are both equal to 0. There is another part to this, which there's three separate cases that we need to consider. But then we're told after that, interpret your results geometrically. Okay? Which means that we need to know then effectively what are the possible forms of the matrix under these conditions. So initially, as I went through this problem, this is where I stopped, but then later on I had to come back to figure out what the matrices actually look like. So let's have a look now at this stage, what the possible forms of A are going to be, given that we know that a plus d is equal to 0 and b equals c equals 0. So that means that a must be equal to a, 0, 0, and because a plus d equals 0, d must be equal to minus a. Okay, so if this is to be idempotent, by the way, a can be equal to 0, or it could be greater than 0, less than 0, whatever. If this is to be idempotent, then it must satisfy effectively this relationship here. And in which case we'll get that a squared must be equal to a. Remember, b and c are both equal to 0. But we'll also get that d squared, and since d equals minus a, that means that d squared is going to be equal to a squared, but d is just equal to minus a. So we get a kind of a contradiction here, almost, in that we require that a squared be equal to a and a squared be equal to minus a for this matrix to be idempotent. The only way that can happen is if a is equal to 0, which also means, by the way, that d equals 0. So there's only one possible matrix that we can have with these conditions, and that is A equals the 0 matrix, which is idempotent. It satisfies this relationship, but that's the only possible form that we can have for a matrix under these conditions here. So how do we interpret this matrix geometrically? Well, the 0 matrix, all it does is just take the whole space, any point in the space, in this two-dimensional space, and just collapse everything down to a single point. That's the geometrical interpretation. So now let's move on to the second part, the second case. I'm going to have to bear that in mind as well, that matrix. In fact, I'm going to make a note of it up there. So for case 1, the only matrix that we that we have is 0, 0, 0, 0, because we're going to need to find out the possible eigenvalues further down the line of the idempotent matrices. Which is not difficult to do, but we need to keep track of them. Okay, so case 2. So in case 2, what information are we given? I can't remember. A plus D. So we're told that A plus D is not equal to 0. B is not equal to 0. But C is equal to 0. Okay, coffee time. So, since we know that B is not equal to 0, then if we think back to those equations that I've rubbed off now, we had one that was B times A plus D equals B. And previously I was warning that in this case, unless we know that B is not equal to 0, we can't just cancel through by B. Well, here we're specifically told B is not equal to 0. So what does this imply? Cancel through by B, A plus D must be equal to 1. So that means in this case that D is equal to 1 minus A. But we also know that C is equal to 0. So since C is equal to 0, that means that B times C is equal to 0. Now, if we think about the equations that we had one that was A squared plus BC equals A. Well, that means that this reduces to A squared equals A. So that means that either A is equal to 1 or A is equal to 0. We can do a similar thing for D, in the sense that we get D squared plus BC equals D, which implies that D squared equals D, which implies that D equals 1 or D equals 0. However, if A equals 1, we know then that D must be equal to 0. And similarly, if A equals 0, then D must be equal to 1. So if A is equal to 1 and D is equal to 0, we get the matrix 1, B, C is equal to 0, D is equal to 0. That's the form of the matrix that we're going to get if A is equal to 1 and D is equal to 0. Now, on the other hand, if A is equal to 0, then that means that D is equal to 1. And the possible form of the matrix that we get is 0, B, 0, 1. This is what we were required to show in the problem. So it actually says here, show that if A plus D is not equal to 0, B is not equal to 0, and C equals 0, then either A equals 1B0, 0 or 0B0, 1, which is what we've shown. Geometrical interpretations of these, well, okay, if I apply this to the vector xy, then what do I get? I get x plus by 0. So what this does is it crushes everything down, the whole space down onto basically the x-axis, because we've only got an x component, and the only non-zero component of this resulting vector is basically the first component, the x component. So everything's going to get crushed down onto a line which is the x-axis. Remember, any linear transformation has to it keeps the origin invariant. So it wouldn't be possible for me to have a line that was off that didn't pass through the origin. So it has to pass through the origin. And because the determinant of this matrix is 0, then we know that the resulting linear transformation is not invertible. So we can't find an inverse matrix for the kind of reverse linear transformation to take us back. If the determinant is 0, that has a tendency to kind of squash things down in a certain sense. So if you've got a 2-dimensional shape, it'll get squashed down to a 1-dimensional shape. If you've got a 3-dimensional shape, if you've got a 3x3 matrix, it will tend to get squashed down to either a 2-dimensional space or a 1-dimensional space, or possibly even a 0-dimensional space. Everything could get squashed down to a single point, the origin. On the other hand, what happens here? X, Y. So what do I get? B, Y, and Y. Okay, so this is going to be a line through the origin. X, Y. So the whole space is going to get compressed effectively onto this straight line. So the whole 2-dimensional XY plane gets squashed down onto this line. Effectively, all of the points on this horizontal line will get, I think, put on. They'll end up here at this point. So all of these points, because the y coordinates of all of these points are the same, they'll all get squashed onto this single point. And similarly, all the points on this horizontal line will get squashed onto this point. So you can see how the whole space is going to get squashed onto this single straight line. So that deals with the second case. So we need to make a note of these possible matrices. So what do we have? 1b, 0, 0, and 0b, 0, 1. And we could also deal with the case where b is equal to 0 and c is not equal to 0 in an identical way, in which case we'd get effectively 2 more matrices, 1c, 0, 0, and 0, c, 0, 1. So I'm going to include those as well, because it's basically an identical calculation that you'd need to do. Now we move on to the third case. There's a lot more involved in this case, by the way, this third case. It's going to take me some time to get through it. And it's this one that really, the first 2 cases were straightforward. It's this third case that really presented a bit of difficulty for me. Really sussing out how exactly I was going to do what I was being asked to do. Okay. So in this third case, we are told that if a plus d is not equal to 0, show that BC is less than or equal to a quarter. Okay, so whereas in the second case we were specifically told if a plus d is not equal to 0, b is not equal to 0, and c is equal to 0, or kind of vice versa, if c is not equal to 0 and b is equal to 0. This doesn't have any specific conditions on B or C. So I split this down eventually. So initially, there was not necessarily any indication to me what I needed to do. It took me a while to kind of figure out that how to. I guess I needed to do some sort of case analysis. So case analysis is where you split things down. You've got a category of a certain type of object, but within that you've got certain sub-objects. So think about mammals, for example. There's different types of mammals. There's different species or whatever, different categories. But within each category, there's subcategories. So I don't know what. In mammals, there's the cat family, or the felines, whatever they're called. And within those, there's lions, there's tigers, there's domestic cats, and so on and so forth. So the idea is that you've got this kind of big category of objects, but then within that, you've got subcategories. And rather than trying to deal with them all at the same time, it might be necessary to kind of subcategorize in a particular way, and then deal with each of these subcategories separately, and by means of which you will end up with a better picture of the whole category. You might be able to show something is consistent within each of those subcategories, and therefore is consistent with respect to the whole. This is a very common technique in mathematics, and I imagine in other fields of work as well, where you can kind of subcategorize things. So the subdivision that I came up with was either if A is our idempotent matrix, the determinant of A may be 0 or it may be 1. How do I know? Well, if we think about this, a squared equals a, the determinant of a squared is equal to the determinant of a squared. Okay, this is straight from the property that the determinant of a times b is equal to the determinant of a times the determinant of b. So the determinant of a squared is equal to determinant of a. So that means that if these two are going to be equal, I need that the determinant of a squared be equal to the determinant of a. Well, this is basically just a quadratic equation. It's just a quadratic equation, x squared equals x, which has solutions x equals 0 or x equals 1. So therefore, the determinant of a can either be 0 or it can be 1. It can't be anything else. And this is how I started my categorization. Okay, so what I did then, if determinant of a is equal to 0 and a plus d is not equal to 0, well then I can further subcategorize into, if determinant of a is equal to 0, then either a times b is equal to 0, or on the other hand, a times b is not equal to 0. Okay, I'm not saying that this is the only categorization to go for, and it took me a while to figure this out, by the way. So I've got several pages of things that I attempted to do, various calculations, before it became evident to me that this was going to be something useful. So this is not something that just popped into my head straight away. This is something that gradually came to me, or was gradually revealed to me through the calculations that I was trying to do, that this might be useful. Now, other people might come up with other categorizations. This is all part of the problem solving process, that there's potentially always a better way of doing something. And mathematicians will strive to find that better way to a certain extent. But just because you find a solution to a problem doesn't mean that it's going to be the best solution to the problem. As far as I'm concerned, I've solved this problem. I'm happy with my solution to the problem. If I was really inclined to do so at this point in time, then I might look for ways that I can improve it. And I do encourage that, but it does take time, and there's only 24 hours in a day. So I don't necessarily have time to fully analyze all of my solutions to all of my problems. When I can do that, then I will do it. Okay, so A equals 0 then. Right, okay. So in this case, if sorry, that should be AD, not AB. It's a correction. AD is equal to 0. Because if the determinant is equal to 0, the determinant of this matrix is AD minus BC. That must be equal to 0. If I know that AD is equal to 0, this implies that BC is also equal to 0. So if BC is equal to 0, I don't really want to be considering the case when one of these is potentially non-zero, because we've already done that in case 2. We've already considered the case if B is not equal to 0 and C is equal to 0, or if C is not equal to 0 and B is equal to 0. So I really want to think about what happens when B and C are both equal to 0. So if B and C are both equal to 0, then what happens here? What are the possible matrices that I can get? Well, if AD is equal to 0, that means that one or both of A and D must be equal to 0. But because I also know that A plus D is not equal to 0, that means that they can't both be 0 simultaneously. So if A is equal to 0, D must be non-zero. If D is equal to 0, A must be non-zero. Okay, but we know that B and C are equal to 0. So the possible matrices are A, 0, 0, 0, and 0, 0, 0, D. Now, if these, remember A is non-zero in this case, D is non-zero in this case. If this is to be idempotent, going back to the equations that need to be satisfied, we know that A squared must be equal to A. Since A is non-zero in this case, A must be equal to 1 for this to be idempotent. And similarly, over here, D must be equal to 1 if this is to be idempotent. Okay, so these are the possible forms of matrices in this particular case. And it's going to be worth me making a note of those cases. 1, 0, 0, 0, 0, 0, 0, 1. Okay, geometric interpretations of these matrices. 1, 0, 0, 0, xy. That's just going to give x 0. So that's going to have the effect of taking the whole space and squashing it down onto the x-axis again. Okay, so this is my x-axis, this is my y-axis, everything gets squashed down. So everything with the same x coordinate. So all of these points here on this vertical line are all going to get squashed down onto this point here on the x-axis. Similarly, over here, for this matrix, xy, that will be 0, y, naturally. All of the whole space will get squashed down onto the y-axis, and all of the points on this horizontal line will all get squashed onto this point, for example. Okay, so they're the geometrical interpretations of those matrices. Okay, so moving on then. What happens now? What happens if we stick with A plus D is not equal to 0? But in this case, now we need A times D is also non-zero. Okay, so in this case, again, we've got AD minus BC equal to 0. AD is non-zero in this case. So that means that BC is not equal to 0. Okay, so that means that either B or C here is not going to be equal to 0, possibly both. Again, we've already kind of considered the fact that the possibility where one of these is going to be equal to 0. In fact, that's irrelevant in this state, at this point. B times C is not equal to 0. They've both got to be non-zero. Okay? So B and C are not equal to 0. Okay, so we're given it, by the way, for this, we're given a hint. We're asked to show that if A plus D is not equal to 0, then BC is less than or equal to a quarter. Hint, find a quadratic equation with roots A and D. This is what took me a while to figure out, how this hint is going to be relevant. Because it turns out that that hint is relevant to this part, what I'm about to do now. So, there's a couple of ways actually that we can arrive at this inequality BC is less than or equal to a quarter. If we take the hint literally, then we get this. Quadratic equation with roots A and D. Well, that's going to be x minus A, x minus D equals 0. The roots of this are A and D. Expand out, I get x squared minus A plus D plus AD equals 0. We know that AD is equal to BC. That comes from this. So x squared plus BC equals 0. And because B and C are both non-zero, let's think about our equation B, A plus D equals B that needs to be satisfied for this to be idempotent. If B is non-zero, we get A plus D is equal to 1. So therefore, here we get x squared minus x plus BC is equal to 0. Because the roots of this equation are real, not necessarily distinct, but real, that means that the discriminant of this quadratic must be greater than or equal to 0. So minus 1 squared minus 4 times 1 times BC must be greater than or equal to 0. Which means that 1 is greater than or equal to 4BC. So BC is less than or equal to a quarter. So we've proved our inequality that we needed to prove. Okay, so as far as we're concerned, we're kind of done there, except for the fact that we do also need to figure out what the forms of the matrix A are going to take at this stage now, and also possibly a geometrical interpretation, although it's not going to be, it's going to be less straightforward in this case to figure out a geometrical interpretation. But okay, let's get rid of that. So going back again to our equations, we know that one of the equations that needs to be satisfied is a squared plus bc equals a, which gives us a squared minus a plus bc equals 0. So if I look at this as kind of a quadratic equation, I can figure out what the value of a is going to be in terms of b and c. We're going to get a is equal to 1 plus minus the square root of b squared minus 4ac over 2. Okay. Now, we also know that, where did I write it? A plus d is equal to 1. That means that d is equal to 1 minus a. So if a is equal to 1 plus minus this thing, then d is going to be equal to 1 minus plus square root of 1 minus 4bc over 2. Okay, so in other words, when a is 1 plus this, d is going to be 1 minus this. And when a is 1 minus this, d is going to be 1 plus this. So that's why I've written the signs that particular way around. Okay, if you can see now then, because again, a is real. So that means that a has to be greater than, the number under this square root symbol here has to be greater than or equal to 0. Otherwise, we start getting into complex numbers and things like that. Well, okay, so that means that 1 minus 4bc has to be greater than or equal to 0. Well, that's what we were getting over here. And we get bc is less than or equal to a quarter. So that gives us two ways, potentially, of showing the fact that bc is less than or equal to a quarter. This is taking the hint very literally. This is also a quadratic equation, though. If we view a as a variable or just an unknown, an unknown, then this is still a quadratic equation. So what it means exactly, I don't know, whether it means this or whether it means this, but they both work anyway. So what are the forms of the the matrices at this stage? Well, we can have a equals 1 plus minus the square root of 1 minus 4bc over 2, b, c, and 1 minus plus the square root of 1 minus 4bc over 2. Okay, so there's two possible forms here, effectively. The determinant is equal to 0. So that means that whatever this geometric transformation represents, it represents taking the whole space and squashing it onto a particular line. It probably wouldn't be too difficult, actually, to figure it out. I'm not going to bother right now, but it's going to be a particular line that the whole space is going to get squashed onto. I'll leave you to figure that out if you want to do so. But that's that's another part of this is case 3, by the way. I forgot to update that. Case 3. This is another part of case 3 dealt with. We've still got some more to go. So now we need to look at what happens when the determinant of a is equal to 1. Okay, so let me get rid of all of this business. So determinant of a is equal to 1. And again, we've got a plus d is not equal to 0. So determinant of a is equal to 1. Okay, so again, I'm going to go for the categorization or the subcategorization AD is equal to 0. What happens if A times D is equal to 0? Then because the determinant of this is going to be AD minus BC equals 1, that means that C is going to be equal to minus 1 over B. So what are the possible forms here? Again, A times D equals 0 means that one of A or D, but not both, simultaneously going to be equal to 0. Can't both be simultaneously equal to 0 because we need A plus D non-zero. So we've got either A, B, minus 1 over B, 0, or 0, B, minus 1 over B, D. And it turns out that neither of these are idempotent. If you square this matrix, it's not possible for it to be equal to this. Similarly with this. I'm not going to go through the calculation, but they're not idempotent. So this is not a possible case that we get anything from. Okay, so moving on. What happens if A times D is non-zero? Okay, so if A times D is non-zero, then either one or both are So we can have, for example, I'm going to do this. A times d is non-zero. Oh yeah, sorry. So again, a further categorization. So we've got either BC is equal to 0 or BC is not equal to 0. Okay, so if B times C is equal to 0, that means that we can have either B equals 0 and C non-zero, or C equal to 0, B non-zero, or both equal to 0. So BC equals and AD equals. Sorry, I'm just looking at my notes here because. Yeah, right. So, because AD minus BC is equal to 1, and if BC is equal to 0, that means that AD is equal to 1, and that means that D is equal to 1 over A. Okay, so what are the possible cases here? Well, we can have A, and let's say we've got the case where B is non-zero, C is equal to 0, D is equal to 1 over A. Or we've got the case A, 0, C is non-zero and 1 over A. Or we've got the case A, 0, 0, 1 over A. Okay, for this to be idempotent, this would require B to be equal to 0. So that reduces to that case. If this is to be idempotent, that would mean that C is equal to 0, again reduces to this case. And if this is to be idempotent, this implies that A has to be equal to 1. Remember, we've got to have the equation A squared equals A satisfied. But because A times D is non-zero, A can't be equal to 0. The only solution is A equals 1. So the only matrix that satisfies these conditions is 1, 0, 0, 1, the identity matrix. That's the only possible matrix in this case. And finally, so we've looked at the case when either at least one of, where AD is not equal to 0 and at least one of B or C, B and or C, is equal to 0. But what happens in the case when we've got AD not equal to 0 and B and C both non-zero? So this is just how it is sometimes with case analysis. You've got you split things down, you've got to split things down again and then again, and this is just how it is. There's as I've said before, there's probably a better categorization, but this is the one that I came up with. It's just how it is. Okay, so if B and C is not equal to 0, then we get B is, of course, not equal to 0. C is not equal to 0. Going back to our equations, B times A plus D equals B. This implies that A plus D is equal to 1, and therefore D is equal to 1 minus A. So our matrix is going to look like A, B, C, 1 minus A. Okay. Now, okay, so if D is equal to 1 minus A, that means that, again, I'm looking at my notes, A squared plus, referring to the equation A squared plus BC equals A, then we get A squared minus A is equal to, plus BC is equal to 0, and therefore A, 1 minus A plus BC is equal to 0. Sorry, no, I've made a mistake. Yeah, sorry. So we get BC equals A minus A squared. So therefore BC equals A times 1 minus A. So therefore BC equals A times D. And that means that AD minus BC is equal to 0, which contradicts the fact that our determinant is equal to 1, because this is the calculation that we would do for the determinant of this matrix. So therefore, this is not a possible case. There's no possible idempotent matrices that come from this case. Okay, so we've got all of our possible matrices. There is one that I've missed off, and it was that, what was it, A plus minus the square root of 1 minus 4bc, bc 1 minus plus the square root of 1 minus 4bc over 2, sorry. They're all the possible forms for our idempotent matrices. We did prove that BC is less than or equal to a quarter. Of the possible cases, so here we shown BC is less than or equal to a quarter in this case. In the other cases, we get BC is equal to 0, which of course is less than a quarter. So we proved the inequality. We've also given a geometrical interpretation. Well, actually, I didn't give one of this. This is the identity matrix, which just keeps the space as it is. It doesn't change anything. Every point under this linear transformation just gets mapped onto it's the exact same point in the space, effectively. Okay, so once we've done all of that, once we've found all of the possible all of the possible idempotent matrices, or forms of idempotent matrices, the next thing that we're asked to do is to find the possible eigenvalues. So to find the eigenvalues of a matrix, just to remind you, we would start out, we would find the determinant, the solution to this equation, the determinant of A minus lambda, B, C, D minus lambda equals 0. We'd solve this equation. How this comes about, I'm not going to explain in this video, but this is how we find the eigenvalues, because what we're trying to find are non-zero vectors which solve such that our matrix multiplied by, or say multiplied by, our matrix multiplied by that vector is just equal to a constant multiple of that vector. We're looking for non-trivial solutions to that. Lambda could be real, it could be complex, it could be 0, it could be non-zero. But the values of lambda that we find are called the eigenvalues, and we can find some corresponding vectors called eigenvectors. I'm not going to go into that too much in this video, but in each of these cases, I'm not actually going to go through it. In each of these cases, what we'll find is that either lambda equals 0 or lambda equals 1. So if we take, for example, this one, 1, 0, C, 0, we consider the matrix 1 minus lambda, 0, C minus lambda. The determinant of this is 1 minus lambda times minus lambda equals 0. The two solutions to this are lambda equals 0, lambda equals 1. In the case of the identity matrix, we'd get a repeated lambda equals 1 or lambda equals 1. In this one, it's going to be a bit more fussy, but we'll still get lambda equals 0 or potentially lambda equals 1. I've got to be honest with you, I haven't actually done the calculation for this one explicitly, but it's going to be these values that we get cropping up. This one, the eigenvalue is going to be 0 repeated. So we're never going to get any other values other than 0 and 1. What might vary is whether we get 0 as a repeated root to this is called the characteristic equation. Either we get 0 as a repeated root, we get 0 and 1, or we get 1 as a repeated root. They're the only possibilities. So that brings us to the end of this particular solution. to this particular problem. So it's been a long solution to this problem, but it was a good, challenging problem. It did take me a while to get there, not only in this video, but actually as I was working through it myself, trying to figure out exactly what I needed to do. There is a lot of stuff. Believe me when I say that this solution didn't just pop into my head straight away. This is perfectly normal with problem solving. That the way to solve the problem is something that gradually emerges. You've got to persevere. You've got to analyze what you're doing as you're going along. Really try to be analytical, and if something's not working, there might be something still that you're doing right, but you just need to be doing it in a slightly different way. And this is what I kind of was experiencing as I was going through my solution to this problem. There was things that I was kind of doing right, but I needed to be doing it slightly differently in order to take me in the right direction. It helps if you kind of have an idea where you're going. Sometimes it can take a while for you to figure out what that direction is, but with a bit of perseverance, you'll eventually get there, in the vast majority of cases. So that brings us to the end of this video.